Hello. Dear guests, students, and colleagues, my name is Professor Washington Yoto Cheng. I'm the current head of the Department of Civil and Environmental Engineering here at Imperial College London. It is my absolute pleasure to serve as the chair of this evening's event and to welcome you to this professorial inaugural lecture of Professor Michael Templeton, our Professor of Public Health Engineering here at Imperial. Whether you are here in person or joining us online, you are most welcome, and thank you very much for attending. I understand that some of you have traveled from as far away as Canada and Nepal to be here this evening, which is absolutely fantastic. This evening, I'm being ably assisted by two members of Professor Templeton's research team, PhD student Maria Koloru, sitting in front here, and postdoctoral researcher Laura Sioni, who's also sitting here. And they will be managing online participation today. Professor Templeton has agreed to a short Q&A session following his lecture. So those online, please type your questions in the chat, and we will look after them during the session. Now, before I say a few words, as you would expect me to do, about Professor Templeton, we all know as Mike, some housekeeping matters. In the event of a fire alarm, please follow the emergency exit signs to leave the lecture theater. The assembly point is on the corner of Exhibition Road and Imperial College Road. And please also note that this event is being recorded. So a few words about Mike. So Mike was raised in St. John's, Newfoundland, Canada, and completed his bachelor's and PhD degrees at the University of Toronto. His PhD investigated the ultraviolet disinfection of viruses in turbid drinking water under the supervision of Professors Bob Andrews and Ron Hoffman. In 2006, Mike moved from Toronto to London. He saw the light to take up a lectureship in our department. And he was subsequently promoted to senior lecturer in 2011, reader in 2015, and full professor in 2019. Now, during his time at Imperial, Mike has established himself as an international leader in the field of water quality and sanitation for developing countries. Mike has shown himself to be especially adept at forming interdisciplinary partnerships, combining his engineering knowledge and expertise with contributions from researchers in medicine, public health, and natural and social sciences. He has led collaborative research and co-authored publications with academic and non-academic colleagues in the UK and in a large number of low-income and low to middle-income countries, including Ethiopia, Tanzania, Ghana, Sierra Leone, Cote d'Ivoire, Senegal, Benin, India, Nepal, and I'm still waiting for Kenya. Didn't find it there. Mike is a chartered civil engineer and a fellow of the Institution of Civil Engineers since 2016. He has served on a number of influential strategic advisory groups, including for the World Health Organization, the Ethiopian Federal Ministry of Health, and the £1.5 billion UKRI Global Challenges Research Fund here in the UK, as well as on technical review panels for the Research Councils of Sweden and Canada. As of March this year, Professor Templeton became the Oxfam and Water for People Royal Academy of Engineering Research Chair in Global Sanitation Technology, which is a very prestigious award and a well-deserved recognition of his standing in this important field. I believe that Mike will be telling us more about the exciting new venture tonight, or this exciting new venture tonight. Mike has received many awards and accolades, including the Stephen K. Dental Award for Global Outreach of the Association of Environmental Engineering and Science Professors. And dare I say, he is the first non-US-based recipient of this award. In addition to his research and global outreach excellence, Mike has also been a valued colleague and leader in our department and across the university as a whole. Mike consistently ranks as one of our most popular lecturers, with our students, and he has been a central part of our undergraduate leadership team since 2013. He first served as our senior tutor until 2015, and then as our director of undergraduate studies from 2016 until earlier this year. In the director role, he was crucial in helping us to navigate the challenges of continuing to delivery of our world-leading program during the very challenging COVID pandemic. Recently, Mike has also taken on the role of co-chair of Imperial College London's Global Development Hub, which is a cross-faculty hub which was launched by the Deputy Secretary General of the United Nations last year and aims to enhance Imperial's research, education, and translational contributions towards helping developing countries to meet the UN's Sustainable Development Goals. And this is by addressing challenges that affect the poorest and most marginalized people in society. I think you can tell the theme of where we are going with this, not forgetting the developing world. It is therefore my pleasure, and it is a great pleasure and honor because I basically I've valued Mike's contribution since I became head of department in September. And so it's my absolute pleasure to invite Professor Michael Templeton to please step up and deliver your inaugural lecture. Mike.
Wow, thank you very much, Washington, and thank you to everybody who's here in person and online. Your attendance tonight is really going to make this a very special evening for me, so thank you very much. So I think, let's just see if the AV works here. Nope. So that was Washington's welcome. So, Pitfalls and Progress. So the title I've chosen pretty carefully with those words, because I think it's been a really hard time the last few years, and I think a lot of people are suffering from a lot of anxiety and depression about the state of the world. And sometimes, you might think sanitation is probably going to be a pretty heavy subject for a Wednesday evening lecture. And sometimes I think you can be a bit discouraged by the state of progress towards things which we all take for granted and which we might consider to be sort of fairly basic things that we should have accomplished by now. So I didn't want to just focus on the pitfalls and the reasons why we haven't got there yet, but also the progress aspect and some good news stories. And hopefully paint a picture of where we're going to go in the next few years to get even closer to universal access to sanitation. I also chose those two words because I think they tell a little bit about myself. So pitfalls is a pun, if you haven't already figured that out, because we're going to be talking about pit latrines a lot in this lecture. And I do enjoy an occasional pun, so you're going to see a few of those in the lecture. I get it from my father, so if you want to get some more good ones in the reception afterwards, go speak to him. And progress, because I think what that says about me is that I'm an optimist. I think people who work with me would tell me that I'm an optimist. They tend to look on the bright side, think that things are going to work out. And really, I think that's why I went into engineering originally. I think engineering, by definition, is a discipline which is inherently optimistic. We have this belief that we have the skills and the knowledge and the creativity to be able to solve major problems. And that's why most of us went into engineering in the first place. So that's the vibe and the theme for tonight. So get on board with that. It's about optimism and it's about puns, okay? So as Washington said, the title I chose for my professorship was Professor of Public Health Engineering, and you might say, well, what does that mean anyways? And it's actually quite an old field of engineering. So we've actually been teaching public health engineering in the Department of Civil Engineering at Imperial for over 70 years, I think now. And our current master's program in environmental engineering is what that evolved into eventually. And I think I've chose that because a lot of the research that I do is directly with health and protection of public health as an outcome in mind. I particularly like this definition, which I found online. So public health engineers maintain and manage a healthy environment within the community through the design of systems and development of policies and procedures to help prevent injury and sickness. Public health engineers protect and promote health. They solve problems that relate to public health, environmental health, and management of waste. And so specifically, how do public health engineers do that? Well, particularly, they tend to know a lot about a few sort of scientific subjects like microbiology in a very applied way, as well as applied chemistry, and also about hydraulic design. So those are sort of the tools that a lot of public health engineers use to then solve real-world applied problems. So how did I get into public health engineering? Well, as Washington said, I left home when I was 17 to go to Toronto to do a program called Engineering Science, or NSci for short, which was a great program because in the first 2 years, they expose you to all types of engineering. So I did mechanical, electrical, chemical engineering, and then in the last 2 years, you have to specialize. And initially, I thought I wanted to be an aerospace engineer when I went there, even though I was never going to be an astronaut because of my terrible eyesight, and I'm too tall anyways to fit into any spaceship. But I really found inspired by some of these subjects like chemistry and microbiology more so than physics, which is what mostly aerospace engineering was about. And I had the pleasure to meet these two guys, Bob Andrews and Ron Hoffman, who Bob came from a consulting background and really taught me a lot about the importance of communication and really clear communication, actually, and making sure that, if you're talking to a client when you're consulting, that they understand exactly what it is you're saying. And I think that translated into them being quite good academics also and good teachers. And I also just got on with them personally because they're nice guys too. So after my undergraduate, I stayed on and I did a PhD with them. And it so happened that in the third year of my undergraduate, there was sort of a big crisis in Canada, which you might not have heard about over here, but it was big news in Canada. It was called the Walkerton water crisis, which was when, basically because of a failure of the disinfection system on a water supply system, about 2,000 people got sick and 6 people died. That really sparked a lot of reviews about how we protect public health and treat drinking water in Canada at the time. So this was around the time when I was sort of thinking about what kind of engineering should I go into to have sort of the biggest impact. And so initially when I was in Canada and the UK, and I'm sort of just explaining this to give you some background before we get into the main topic of tonight, which is sanitation for developing countries, where I sort of took a lot of the skills and the knowledge from the earlier research and brought that into a different context. But my PhD in Canada was about viruses in water. And it turns out that viruses, when they're in water, they're quite often attached onto particles. So they're not free-floating, but they're attached onto things. And that actually can make them quite difficult to disinfect in some cases if you're trying to kill them, because they get blocked, they get protected by the particles. But the picture there shows is from my PhD thesis, where I was taking electron microscope pictures of different types of viruses that I was using in my research. Different shapes, some of them sort of the round-shaped one there, which was quite a small one, and then ones with tails on the end of them, which were about an order of magnitude bigger, and tried to understand what are the particle characteristics and virus characteristics that lead to protection of these viruses from disinfection. And so really one of the recommendations that came out of that research was that you really have to do a good job of trying to remove as many of the particles before you disinfect the water, and also that certain types of particles are particularly problematic if you're trying to disinfect water. Another great opportunity in my PhD was to get out of the lab and to actually do things at scale. And so I think that was another really valuable experience, was to have the opportunity to do what we call pilot scale research. And I worked with a company called Suntech Environmental, who design ultraviolet disinfection systems for water and wastewater. And what they were interested in is designing these reactors. So those are UV lamps that you're looking at there. And the water would flow past these lamps for a few seconds and get completely disinfected by the lamps. And they were interested in sort of what should be the flow rate through the reactor, how far apart should the lamps be, how bright do the lamps have to be in order to properly disinfect this water. And they set up a test center, and me as a PhD student, I got the opportunity to run this test center. And they basically had 2 sort of swimming pool-sized tanks, an inlet tank and a waste tank. And they set up a pump, a massive pump, and a few valves, and the water ran through the UV reactor. And they said, Mike, what we want you to do is to grow some virus in your lab in Toronto, drive out to this test site, dump the virus into the inlet tank, dump some other things into the tank to simulate different types of water, and then, yeah, push the water through the reactor and see how well the reactor does at killing the viruses. And it was kind of a fun exercise because this pump could go at about 1,000 gallons a minute or something like that. So I would, drop the virus in, open the valve, turn the pump on, run around to the other side of the reactor with my PPE on, get some samples from the outside of the reactor, run back, adjust the flow rate again, and hopefully get enough samples before the water in the inlet tank got all the way down to the level of the pump. And after a few months, I more or less had it nailed. So as I said, it was a really good education in terms of some of the challenges you face when you take concepts that are neat and tidy in the lab and then applying that in a real flow-through, more realistic kind of condition. And so that helped them then to design, what the proper spacing of the lamps and appropriate flow rates through the reactor should be. This isn't going to be a hugely technical lecture, so don't worry too much about this chemical reaction here. But another aspect of the research that I did in Canada and continued on with the water companies here in the UK initially when I moved to Imperial was that they're quite interested in what are called disinfection byproducts in water. So when you add chlorine, for example, to water, it reacts with a lot of compounds which are just naturally present in water. They come from decaying leaves, or they might leach out of soil into water. And it turns out that a lot of those organic compounds, they react with chlorine to form all kinds of byproducts, some of which we think they're either known or they're suspected to be carcinogens or have other types of health problems if you're exposed to them over a lifetime, for example. So it's kind of a chemist's dream because you can take different types of organic compounds, disinfect them under different conditions, different pH and disinfection type conditions, and measure all of the the byproducts that come out of that. And I think to date, people have now identified over 700 byproducts that are found in tap water because of these types of reactions. So it was quite an interesting line of research, and there's people studying this still today in countries around the world. I kind of found it a bit frustrating as a topic, though, because we don't always have the health information to really say whether these compounds are a real problem or not. It's quite a difficult thing to nail down and say we should be worried about this or not. But from a chemist standpoint, it's kind of a dream. If you want to publish lots of papers, this is a really good topic to be in. But how did I get into sanitation research specifically, which is the topic of the lecture today? So it kind of happened by happenstance initially. So Howard Wheater, who was the head of the environmental section in our department when I first came to Imperial, and he subsequently went in the opposite direction to me. He's now a professor in Canada. He sent me an email. He met me when I first arrived, and he sent me an email, and he said, I've been in touch with these folks in Nepal. They'd really like to put in a proposal for a British Council grant. And Mike, this might be something that you might be really interested in. And I was really grateful to Howard because it was a very generous thing for him to do as a professor to support a new lecturer. And that's where I met Sabitri, who you're going to hear from a bit later today. And that was really my first foray into this topic, and the first time I really had been to a developing country before. And really, I think going to Nepal and then going to a few of the other countries in the sort of global south where I do a lot of work now, it really hit me that a lot of the skills that we learn as environmental engineers and public health engineers can have huge benefits in the developing world. North Americans like to simplify things numerically by referring to school bus equivalents. It's a typical sort of analogy. But it's a very sad truth that the equivalent of about 2 school buses full of children under the age of 5 will die over the course of the next hour because of diarrhea from dehydration, basically, because of lack of access to adequate water, sanitation, and hygiene. And thinking about it another way, it's also true that 3.6 billion people don't have access to what's called safely managed sanitation. So in other words, they either don't have any toilet at all, and they practice what's called open defecation, or they have access to a toilet, but it's not a sustainable toilet. So it's just going to fill up, there's no safe way to empty it, and there's no sort of plan to treat the waste at any point. And so we had the Millennium Development Goals in the year 2000, which we didn't achieve by 2015 for access to water and sanitation. And then in 2015, we set the Sustainable Development Goals. And they really, the UN really sort of raised the bar, really, when they set the Sustainable Development Goals, because they now said we're going to go for universal access to sanitation. So we want everybody in the world to have access to safely managed sanitation. And the progress has been very slow, and we're actually quite far behind where we need to be to reach that by 2030, which is the deadline of the Sustainable Development Goals. And I was in Geneva last week with some colleagues from the International Relations Office, and personally I found it a bit discouraging, actually, because I think a lot of the people there, because of what's going on in the world currently, have sort of seen that maybe progress towards the Sustainable Development Goals is being put to the side for a second because there are more urgent things that need to be focused on right now. But the one that my research is particularly looking at is number 6, which is about access to clean water and sanitation. And really the key to achieving this goal is making this system work. Okay, so most people in the world, they don't actually have a toilet that's connected to a sewer. And you could argue that actually it's not really a sustainable approach of sanitation anyways, to be flushing our waste with water, especially if you live in a very water-scarce part of the world where you don't have spare water or water to spare. So if you don't have a sewered sanitation system, you need something like this. So you have some kind of on-site toilet or a septic tank, which eventually has to be emptied safely somehow, and then that waste has to be transported somewhere, and it has to be treated somehow, and then hopefully you can get value from that waste or dispose of it in a safe way back to the environment again. And sadly, this system doesn't work in large parts of the world. And so a lot of people, for example, might have access to a basic toilet, as we see on the left there, but it's not a safely managed form of sanitation because for example, in this case, the toilet has filled up. A lot of the most marginalized people in the world, they live in areas that are prone to flooding also, so these toilets will flood and again become almost a focal point of disease when they're supposed to be something that benefits health, really. In other cases, people have a toilet, but they don't have a safe way to empty it. And that's got to be the worst job in the world and one of the most dangerous jobs in the world for a lot of people around the world who have the job of emptying latrines without any kind of protective equipment. And then even if you do have the luxury of having somebody who's going to empty your toilet for you, in a lot of countries, that waste is emptied from the toilet, but then there's nowhere to dispose of it safely or to treat the waste. So it ends up just getting taken to a river, dumped back into the environment, which really negates the whole public health benefit of having a toilet in the first place. So this is the problem we need to solve. This is the sort of engineering system that we need to make work. And so I'm going to give you a few case studies of some research I've been involved with, which looks at different parts of that sanitation chain. And the first one is a study, a very interdisciplinary, multi-institutional study that I was part of, which is called the Tiger Toilet, which is not a toilet for tigers. It's a toilet which uses tiger worms as part of the treatment system in the toilet. So this was funded through the Bill and Melinda Gates Foundation, who had a Reinvent the Toilet challenge, which you might have heard about. And basically, they were trying to encourage people to come up with designs of toilets that would be more sustainable and last much longer than the currently available technologies before they filled up. And so the idea here was to adapt the basic latrine design, which we saw on the previous slide, by basically making it a good environment for tiger worms, which are sort of like nature's rubbish men, really. They're very good at degrading human waste very efficiently and transforming that into a compost material, which is essentially sterile, so it makes it a much safer environment to empty the toilet. So the aim was, by having these worms in the toilet, reduce the filling rate. So whereas the toilet might fill up after 5 years, can we make it slow down, fill up after 20 years, let's say? Also, the worms, this was sort of not an initial intention, but we found that the worms were so good at degrading the waste that actually there are far fewer smells and flies in these toilets. And as I said, eventually they will fill up with compost, but then it's a much safer process to empty the latrine. So it was really a neat project to be part of because it was highly interdisciplinary. There were design engineers, there were behavioral scientists, engineers like myself, biologists, and many academic and non-academic partners, and there was a huge amount of community engagement in terms of finding out what are the characteristics of a toilet that, that they want, and how much are they willing to pay to purchase one of these toilets. So I'm going to be acknowledging a lot of people throughout the presentation and also at the end, but I have to acknowledge Walter Gibson, who is the leader of this project, and Claire Furlong, who is the postdoc in my group at the time, but she's now one of the world leaders in sanitation at IHE Delft in the Netherlands, and the London School of Hygiene and Tropical Medicine, who were the leading institution on the grant. And so it's a really good example, I think, of what I've sort of coined eye to eye, seeing eye to eye. So it's really taking something from idea to impact. And the project really has two stages that you can think of. It was sort of a four-year project, and there stage one was the first 2 years. Stage two is sort of beyond the first year and a half or 2 years. And initially, we just spent a lot of time talking with partners overseas and here in the UK, and thinking of what are all kinds of different things that we could try out, and also talking with the stakeholders in country to see what would be feasible there. And then, of course, you have to do some robust research to make sure that this idea actually makes sense and it can work. And as I showed earlier with that UV example, not just doing that in the lab, but also doing it at realistic scales. And we did that initially in the UK under fairly controlled conditions. But at the same time, in that early stage, we were constantly engaging with communities in India to understand what were their preferences and constraints for these toilets. And then once we came up with something that worked and that we proved could work, we then moved on to form a joint venture with Indian sanitation entrepreneurs. And this guy, Ajit Og, is now one of the world leaders in implementing these technologies around the world, mainly in India, though. And that then provided a great opportunity for us to do ongoing research. So once these were installed in the field, I could then send students to India and see how they're working in the field and how that compares to what we found back in the UK. And we could share good practice, what's working, what's not working in the field. And now we're really interested in scaling up. So we have a technology that really works well. How do we disseminate it and make sure that as many people as possible who need this toilet are going to have access to it? And a lot of academic research in the field sort of stops there, I would say. So a great idea, you do some lab tests, maybe you do some pilot tests, you publish some papers. That's where the idea sort of stops. I'm not perfect. I'd say a lot of my research has also stopped at that point. But I think, really to have impact, you need to sort of think about engaging with end users, working with international partners, and thinking about things like sharing good practice and scaling up once you've implemented the technology. So initially, we did some hard science, some experimentation in hard science, where we had some controlled experiments. These were conducted out in Wales at the Centre for Alternative Technology there. And we had basically comparison toilets, some that had the worms in them and some that didn't. And Claire Furlong led that work. And we were then able to measure, how much are the worms reducing the fill rate? Are they treating the waste? Are they cleaning up the liquid part of the waste? And what other benefits are they having in the toilet? And this is one of my puns. So people talk about raw data, so I'll call this crude data, because basically what we're showing here is accumulation of poo in the latrines that have the worms, the blue line, and the one that don't have the worms. And our undergraduate projects last for about 3 months. So you can see on the x-axis there, we have about 3 months worth of data from our undergraduate student. And this was very early on in the program, but she showed in a very robust, nice way that you're probably reducing the fill rate by maybe 2/3, at least half, maybe 2/3 by using this, optimizing the worm performance in the toilet. So we did the pilot testing in the UK. It was hooked up, I think, to the visitor center in this center for a while, so people from the general public were using it. And we were able to optimize, how many worms do you need? How should the waste be loaded into the toilet? What temperatures can they sustain? What kind of moisture levels are they happy with? And then then it was about moving out into the real world. And you can see the top there was a lot of consultation with intended end users, and also developing sort of design manuals so that, we weren't interested in intellectual property. We wanted people to be able to take the technology and use it using local worms, local bedding materials, not having to fly anything from the UK or anything, but a really simple way to adapt this latrine. And so if you're actually sitting in a tiger toilet, you would just think it was a normal latrine. So this is the toilet here, and then the worms are in the little side reactor there off to the side. So you have no idea that there are worms underneath your toilet treating the waste. And I had an MSc student who went out there one year, and I told her, I want you to figure out what's the fill rate of these toilets. So she went around to about 15 different toilets in India, and she got the permission of the households to take the lid off and use sort of a laser pointer or a laser measure to model the surface of the waste in these different latrines. And because we knew when the latrines were installed and we had sort of the blueprints of the latrine designs, we could then estimate what was the fill rate of these latrines pretty robustly. And I mean, that seems maybe a bit nerdy and mathematical for something which is quite a crude sort of environment to be studying. But actually, this kind of approach, I think, is really important in development, where there's a lot of sort of anecdotal evidence, and people say this works or this doesn't work. But it's not always studied and published in a really rigorous kind of way. So it's sometimes hard to compare something that works in one setting to a slightly different setting. I'm going to steal a joke from Washington here. So I had another student who he saw the light at the end of the toilet by putting a red light camera into some of these toilets. And these are toilets that had been, so they were seeded with worms about 6 or 7 years ago. The families had been using them. We went back, we took the lid off, and we just wanted to make sure the worm population was still robust and still doing what we thought it was doing without any reseeding of the worms. And I won't play the video. It's maybe not, might take away your appetite for dinner later on. But he basically proved that these worm communities were still very robust, and that actually, because we had a time scale on these videos, we could tell that they were degrading the waste actually much quicker actually than I would have thought that they were. And so during lockdown, one of my lockdown projects, I know some people learned another language or learned the piano or something. One of my lockdown projects was to create an international sanitation association of people who have implemented these tiger toilets around the world. And we called it the International Worm-Based Sanitation Association, IWBSA.org. Not to be confused with IWBSA.com, which is the Isle of Wight Beach Soccer Association. I thought it would be good to have a joint event with them sometime maybe. So .org, if you want to visit it. But this is all about what I was saying earlier about scaling up. We have this great technology. We have evidence that it really works. Now we want to get the word out there, and we want to share good practice, share design manuals, and make sure that we can spread this idea as far as we can. And so far it's been used in 9 countries at least. We think there's at least 200,000 people using them, but actually my colleague in India, who I showed there earlier, told me a few weeks ago that he's just got some major contracts to put in orders of magnitude more toilets to serve many more people than this, actually. So it's a bit hard to quantify, but it is starting to scale up. We think there's about 57 tons of waste globally that are treated by these toilets. And Oxfam have done some sort of economic studies also on these toilets and showed that if you consider sort of the costs over 5 years, it's about a 90% lower overall, maintenance cost over 5 years compared to a traditional latrine. So that's kind of a nice, I think, success story, and it shows that we can make progress if we have the right partnerships in place and we sort of think creatively and we work with partners in the affected communities. The next few slides are about sort of other aspects of sanitation research, which I won't go into as much detail about. But one is the idea that, quite often as engineers, we think we just need to build something and that we build technologies and that the technology will solve the problem. But increasingly, there's a trend to think of sanitation not as just a technology, but actually as a service. In the same way that we think of rubbish or recycling collection in the UK, maybe we should think of, toilet waste collection in certain settings where that makes sense to do that. So this is an example from one organization called Soil, who have implemented this, which is called container-based sanitation. So they provide a service where you don't buy the toilet, you pay a user fee. They provide the container. They look after collection of the waste, transport of the waste, treatment of the waste. And their business model works by creating some kind of a valuable product so that it's a social enterprise, and it means that you can employ people to keep this business going in a circular kind of way. So it's great. It serves people who can't afford to buy a toilet by charging a very low user fee, and it also employs people in the community. and it generates valuable resources, like it could be biogas, it could be a soil enhancer from the waste when it's treated. And this is particularly popular in areas where, for example, either people don't have the legal right to dig a hole in the ground. You know, a lot of the poorest people in the world don't own the land that they live on. So in this case, they're not doing anything permanent to the ground because it's a container that's provided. Also, as I mentioned earlier, a lot of the poorest people in the world live in areas that are very prone to flooding. And again, you don't really want to have a pit latrine if that pit is going to be flooded occasionally and bring the waste back to the surface again. So a container-based toilet is maybe an attractive option in those cases. And so we did a study where we sort of, along with Savitri, who is a co-author, and looked at sort of developing a feasibility study to say if you're going to a new city, how would you be able to tell whether container-based sanitation was going to be attractive in that kind of environment? And these are just some examples of different businesses which have spread it up, which are currently implementing this business model around the world. And I'm always hearing about new sanitation services that are sprouting up using a similar kind of approach. So that's a fairly recent development, actually, I would say. And again, sort of challenging to engineers to think of it not just as something you build, but actually thinking about the whole sort of management and service aspect of it. Another thing I've been looking at is can we recover value from pit latrines? And here I've been collaborating especially with Dr. Jeff Fowler, who's an expert in this process called pyrolysis, which is a method of thermally decomposing waste, degrading waste of various types. And you can conduct this pyrolysis under different conditions to produce different types of outputs. So for example, you could take the waste and pyrolyze it and produce biochar, which could be used as a soil amendment, for example. Or you could run the process in a certain way to produce oil and gas, so as fuel sources from the process. So this is a relatively new idea for applying to latrine waste. It's something that's been used before for quite a long time for sewage sludge and other types of waste. But we're currently doing some research, and my PhD student Maria here is focusing on this for her thesis, if you want to learn more. To look at, how well does this process work if we're using latrines waste from on-site sanitation, and how well does it work if we combine it maybe with other types of waste that these communities might need to treat also, like crop waste or food waste, for example. And then another area of research is all about how do we minimize pollution from latrines from getting into groundwater. This is something I collaborated with Professor Butler, Adrian Butler, who's in the audience also, because there's this big push to meet the Sustainable Development Goals for access to sanitation, but actually if you put a toilet in the wrong place, it can be quite dangerous, and it actually might cause regression in terms of access to clean drinking water if you're going to pollute a well because you put the latrine in the wrong place. And there's quite a lot of guidance out there in terms of microbial pollution of groundwater, but Adrian and I were involved in some research where we looked at maybe how do chemicals from the latrines pollute groundwater. For example, nitrate, which comes from the organic nitrogen in the waste and is a transformation product from that waste. And it's quite a complicated problem, actually. You have to think about the soil characteristics, the level of the groundwater, whether the sort of moisture of the soil, whether the biological processes that are there are going to be the right ones to form nitrate or even to destroy nitrate in the soil. But it's an interesting area, and I've seen in a number of countries where I work in West Africa and also in Nepal, where it's a big problem, actually. They have very high levels of nitrate in their groundwater, which is used as drinking water. And it doesn't come from fertilizers or anything. It comes from latrines nearby. And so that some of these different sanitation challenges are part of the reason why we've got this new research chair, which has been funded. So that tells you a bit about what I've been working on in the past, and for the next 5 years. I'm really excited that the Royal Academy have supported this partnership with Oxfam and Water for People, who are really two of the biggest humanitarian organizations in the world implementing sanitation around the world. And really the 5-year research program is again looking at aspects of this non-sewered sanitation system and coming up with innovations with partners in 5 different countries to address different aspects of that system. So for example, project number 3 there is looking at the septic tank design, which more or less hasn't changed in about 150 years, really. But we need sort of, for example, ways that we can ship the materials to build septic tanks more easily. Oxfam have thought about maybe we could have sort of flat pack septic tank systems, which like IKEA, produce for furniture, that you could easily ship out into the field and would be installed much more easily than sort of a big tank with a lot of airspace inside it, which is not a very practical, it's quite a heavy technology and quite an impractical thing to ship around the world. So yeah, those are some of the projects I'll be looking at. And the last few slides are really about the fact that, and I tell this to the students quite often when I'm lecturing, that as an engineer, you might be working on a particular piece of infrastructure or something, and in my case, as I showed earlier, it might be SDG 6 that I'm thinking of, clean water and sanitation. But really, these goals are closely linked to each other. And so, for example, if I'm building toilets in a school in Ethiopia, and I'm providing gender-segregated toilets, which have facilities for girls, when they reach the age of menstruation, which is quite often when they drop out of school in a lot of countries. That has a big impact on number 5, gender equality, and number 4, quality education, and of course, number 3, good health and well-being also. And sometimes I hear people who sort of despair that it's too expensive to achieve the Sustainable Development Goals, and I think there's a lot of double accounting that goes on because people don't really recognize that there are close links between these goals, and you're actually getting great added value when you address one goal in terms of progress towards the others. And so an example of some of the research that we're doing on this sort of topic is related to this. Well, this photo sort of brought it home for me. So this was a photo that my PhD student, former student Laura Braun, took when she was in Ethiopia. And she showed this to me and said, sort of guess, how old do you think that girl is in the middle of the picture? And I don't know, you might guess 6 or 7 years old, possibly, something like that. And she's actually about 12, that girl. And it's because her growth has been stunted because she's got a number of helminth infections. So she's got a number of worm-based infections, which are because of the poor hygiene and lack of toilets in her school, as you can sort of guess from the rest of the photo there. So that kind of struck home the fact that you're not just building toilets for the sake of building toilets, but it's actually having an impact on the future generations in this country if you achieve that. And so that project that Laura was working on was a particular type of worm-based disease, which is called schistosomiasis. This is a bit of a mouthful to get your mouth around. And in international development, it's what people call a wicked problem. So wicked problems are ones that have been around for centuries or even millennia, and they're very complex, and we haven't been able to really make a dent in solving them. And so I have a picture here of the ancient Egyptians, because people have actually looked at mummified bodies from ancient Egypt and said, oh, they had schistosomiasis back then, which they got from the Nile River, 2,000-3,000 years ago, or no, longer than that ago, actually. And then the picture of, that's Napoleon Bonaparte there on the bottom right, because when the French army invaded Egypt, they noticed that the Egyptians, a lot of the men had blood in their urine, and it was because they had schistosomiasis infections, urogenital infections, causing them to have blood in their urine, and the French army called it the land of the menstruating men for that reason, because they didn't understand what was causing the problem. And a lot of the French soldiers actually contracted the illness when they were there too. So it's something that's been around for hundreds, if not thousands of years. And it's sort of a wicked problem because the life cycle of the disease is very efficient at keeping going. Okay, so if one person is infected, they shed the eggs of the worms in their urine or their feces, and if you don't have a proper toilet, that gets into water bodies nearby, and it infects snails, and the snail acts as sort of an intermediate host, which then releases parasites into the water which infect other people. And it's a really efficient life cycle, which is very hard to break. And the WHO now is really trying to eliminate schistosomiasis, so they want to get down to 0 cases. But we're still at about, I think, 200 million people who are affected by this disease, almost all in sub-Saharan Africa. So to solve the problem, we could give everybody drugs, which is going on right now at very large scale. And the pharmaceutical companies, to their credit, have been extremely generous in distributing deworming drugs. But they're not vaccines, they're only deworming drugs. So if people are exposed to the parasite, they're going to get reinfected, and the whole cycle will continue. We could put toilets in, which would prevent someone from spreading the parasite into water, if you can contain the waste and make sure that it doesn't somehow end up in a nearby river or lake where people would have contact with the water. We could try to kill all the snails, which is another approach that's been used, because if there isn't the intermediate host, the disease couldn't really continue. Or we could look at, if we assume that some of those other solutions are not in place, or they're not going to be in place anytime in the near future, we could look at just trying to make the water safe. So assuming it's contaminated, try to treat the water and understand how we can make the water safe so that people can have safe access to the water. Okay, so again, that's sort of an example, I think, of how the goals are linked, and how as engineers, it's really beneficial to work with people from medicine, behavioral science, understanding why people have contact with water, what are the objections they have to taking the deworming drug, and really working together to implement all of these solutions in tandem so that we can hopefully break this cycle by having multiple barriers to preventing the disease. And so we had a major project funded through the Global Challenges Research Fund called the WISER project, Water Infrastructure for Schistosomiasis Endemic Regions, and had great partners from Ethiopia and Tanzania, and the Natural History Museum, who I have some colleagues here this evening. And so that was a really fruitful, very multidisciplinary collaboration, that project. And with that, I think my second last slide, I'm really pleased that Imperial has recently decided that they're going to pursue a certain institutional strategy, which is called the Global Development Hub, which Washington mentioned, which was launched last year, and it's starting to pick up pace because we're hiring some staff to actually run the hub. But the chair, there's two chairs for this hub. One is me in engineering, and Sarah Fiedler, who's a professor of HIV and communicable diseases in medicine. And it's really looking to raise our game in terms of what we're doing in developing countries at Imperial. There's a lot of great work, actually, that does go on across the college. It's not really all, I say, joined up, I guess. We need to be more joined up, more interdisciplinary. And I think we need to share our partnerships better in terms of who we work with overseas. And the science at Imperial is really great, but sometimes it's the partnerships that we're kind of missing to really have the impact on the ground. So that's the aim of the hub for the next few years, is to boost our impact of the great things that are going on here at Imperial. So my take-home messages. So if you drifted off during the lecture, wake up now. This is what's going to be on the exam. So public health engineering, it's an old subject. We've been teaching it here for over 70 years, but it's really as important globally now as ever. Robust engineering research has to underpin practical solutions, so the eye-to-eye, idea-to-impact that I mentioned. Progress is possible. Don't get depressed. Be an optimist, but it's going to take partnership, not just academic partnerships, but with communities and end users also. And really, sanitation, you might think it's a gross topic, or it's not like building, I don't know, the next moon lander or something, really a really sexy topic, but I actually think it's a really exciting topic, and certainly the impact potential is massive when you think about some of the scale of the problem that I talked about earlier in the lecture. So lastly, I'm going to embarrass a few people and cause some blushes in the room by saying huge thank yous to a few people. And we saw Napoleon earlier in the lecture, and I think there's a saying that's attributed to him when somebody came to him and said, there's this new officer who's really brilliant. And he said, yeah, okay, he's smart, but is he lucky, is what Napoleon asked. And so I've been extremely lucky in my career, and I really have a lot of people to thank for being supportive and allowing me to get here. So first of all, Imperial College for agreeing to grant the chair, recognizing this is an important area of research, and to the whole team here for running the event and organizing the event tonight. Thank you very much. The department, which I think is the best department at Imperial, right, Washington? We're really on top of our game in research and teaching and innovation. And it's really a great group of people, too. I mean, Washington mentioned during the pandemic, as director of undergrad studies, I think I spent time talking to pretty well everybody in the department about their teaching. And everybody really raised their game, including the students. So it's a really a great group of people. Within the department, the section, I'd like to particularly say thank you to. There's a really supportive group of people specifically focusing on environmental and water resource engineering, both the academic staff, but also the non-academic staff and the students in the section. Nigel, I have to say thank you to Nigel Graham when you start at Imperial as a lecturer, they assign you a mentor, who's normally a professor who's very successful. And I was really lucky, again, in the lottery of life, that Nigel was assigned as my mentor. And Nigel really introduced me to everybody I needed to know at Imperial, and also people outside of Imperial. He was very generous with his contacts and co-authoring papers and things. So thank you very much to Nigel, and really just learned a lot about being a gentleman and being nice to people, really, from working with Nigel, because he's a super guy. All the research funders, of course, for providing the money to fund the students and fund all the field work, et cetera, and lab work. My brilliant collaborators from around the world. This is only a few pictures, actually, but all that I could fit on the slide, including Sabitri, who we're going to hear about from in a few minutes on the left there, who looks the same today as about 15 years ago in that project that was taken. Whereas you can see, I'm kind of unusual as a man that my hair gets longer with age instead of shorter for some reason. My exceptional research team. I mean, no academic could actually reach professor level without having wonderful students and researchers. And this is a fabulous thing about Imperial, is the opportunity to work with such brilliant students and researchers from around the world who bring so many creative ideas and really hard work to the research. So thank you very much to all of them. And really, the scenes of graduation are what it's all about for me in the end. And a lot of these students are now their own academics, or they're doing exciting things in industry, or some of them are still at Imperial. But that's really what I think being an academic is about to me, is making sure that you can help other people to succeed in their career. Very lucky in the lottery of life with my parents and my in-laws, who have been very loving and supportive. And I have to, of course, say most of all to my wife, Pom, who's put up with me traveling around the world and sometimes sitting, thinking silently in the sitting room and not talking to her about something research related. So thank you very much to Pom also. And the eagle-eyed of you can see I'm actually wearing the same tie as I am in that picture, because I thought it was a lucky tie. She showed up that day to marry me. So I'll wear it to my lecture today too. That's it for me. Thank you very much.
Thank you very much, Mike. Tour de force, really. I was actually sitting there listening, coming from the developing world, identifying with the problems that Mike has been talking about, recognizing the internationally leading research we're undertaking, but also feeling very emotional about offering real solutions. And one of the challenges always, when I talk to my colleagues, is Imperial being a global top 10 university, our department being a leading department, and having international stars and leaders like Mike, one of the questions I always ask is, what are we doing for the developing world? And Mike is an exemplar. Direct solutions, leveling up, but leveling up globally. So thank you, Mike, for that excellent lecture. Now, the tradition normally is that we don't allow questions during inaugural lectures, but given the importance of the topic, and given that it is Mike, we decided to make an exception. So we're going to have a few minutes for questions. We will take one from the audience and then go online. I think 5 minutes before we go into the vote of thanks. So I'm going to use the chair's prerogative and ask you a question. Out of curiosity, how did you zero in on the tiger worm? How many animals did you test before you got into that? I just would like to know. Thank you, Mike.
So that was a really great project, and again, I can't take credit for it because it was a lot of institutions involved. London School of Hygiene were leading it. We were the engineering component of it. And the great thing about the Gates funding was that really they just encouraged you to be completely wacky. We had a number of brainstorming sessions where we came up with a list of maybe 20 different ideas that might work and narrowed it down to a short list. I was a bit skeptical of worms, to be honest, because I thought, how robust are they going to be? Are they going to survive? If people leave and don't use the toilet for 2 or 3 weeks, are they going to die? Are they going to stop working? But a number of the people who we worked with had some experience with composting, and India, there is sort of a tradition in parts of India of using worms to compost waste, and so we sort of narrowed down on that and decided we would give it a try. But there were a lot of other great ideas that came out of that, which were shortlisted, which are still in the memory banks, which we might test in future. Yeah.
Thank you, Mike. Online, any question online?
Yep, so the first question is, can you give any examples of other worms that can be used other than tiger worms for on-site sanitation?
Yeah.
Same question.
So tiger worms is sort of a general name for a bunch of different types of worms, actually. And we chose that worm because they're a type of earthworm that is more or less ubiquitous around the world. So you don't have to use that particular type of worm. And the whole idea was that people would develop similar technologies using indigenous worms. So quite often when I talk about the tiger toilet, people ask me about, are you going to have invasive species if you fly worms from the UK that are going to take over the environment? And that's not really the idea. The idea is try it with similar earthworms that are in your country. Because quite often, actually, those worms are adapted to the local climate and the local soil conditions anyway, so they're more likely to survive in those kinds of conditions.
Thank you. Question from the audience here?
Stephen?
Yes, Stephen.
Stephen Smith, Mike's line manager.
There's a mic coming to you, Stephen. Mike. Yes.
Yeah, thanks for a great talk, Mike. Here's the question that you wanted.
So can you say who you are?
Yeah, I'm Stephen Smith, Professor of Bioresource Systems and Head of Environmental and Water Resource Engineering. But there are some pretty tough parasites. Some of these fecal parasites, they can survive, the eggs can survive for like many, many years. And, normally you have to provide some pretty extreme physical conditions to inactivate them.
Yeah.
And I just want to do earthworms do the business. I'm thinking about Ascaris eggs. You mentioned Ascaris.
That's an area that we're really interested in studying, actually. So we have limited data so far on Ascaris. It does seem to be very good at sterilizing it from a bacterial standpoint. But you're right that I think the challenge will be the really resistant eggs. Yeah.
Thank you.
Yeah.
There's a question by Catherine at the back. Catherine?
Hi, Mike. In Ireland, there's an enormous number of septic tanks owned by people who are not impoverished. And is there also a way to make money out of this technology in terms of reducing people needing to get their septic tanks emptied in developed countries?
Yeah, absolutely. In fact, I'm actually collaborating with a group in Galway right now, and there's actually a joint EPSRC Ireland funding scheme right now. And something that they actually brought to the table was the fact that a lot of rural communities in Ireland, they don't have the financing or maybe the capacity to have big wastewater treatment facilities, and a lot of people, as you say, are on septic tanks. So we're actually taking a lot of the ideas that have worked really well in India and looking at how well could we translate that to the Irish setting. It's probably going to be more a case of designing sort of centralized facilities with these worms, for example, to empty the septic tanks and take them somewhere nearby. But it's a very low cost, low hands-off technology. So it has a lot of applications in rural parts of the developed world also, I would say.
Thank you, Mike. Online?
So building on that, do you have any opinions or ideas on how engineers and researchers can help break down non-technical barriers? In many cases, we have the technical solutions, but the problems may be financial, cultural, and political.
Yeah, I could give another lecture on that topic probably. But yeah, I mean, I think those aspects are so important, and they need to inform engineering design, really. So, when we were doing this technical brainstorming and narrowed down to the tiger toilet, we were very conscious it has to be something that is cost effective, ideally the same cost or cheaper than the current technologies that people are using. And it also has to be something that's socially acceptable to people. So there's no point designing a technology that they're just not going to accept. They're going to be grossed out by the worms, not going to want to use that toilet. So totally on board with that. And I think that's, again, what I was saying about interdisciplinary partnerships, why they're so important for engineers to understand that you need to work with people from non-engineering disciplines to make sure that these have impact.
Hey, one last question over there, please.
Fayez.
Hi everyone, this is Fayaz Memon, professor at Exeter University. I thought I would be boasting saying that I traveled from Exeter, but here we have people from Canada and Nepal, so I don't say much. It's always good to be here, which is kind of my place of education as well. Back in 2000, I moved to Exeter. As Mike, you have been already alluding on the social aspect. Have you come across any social dimension related barriers for the uptake of what you are proposing?
Yeah, I mean, it's not my focus area. I mean, I'm not a social scientist. And to be honest, there are a lot of experts in the world who really know what they're doing in that side of things in terms of the social science of sanitation, understanding the motivations for sanitation, the willingness to pay. And I sometimes think actually that the technical bit is overlooked actually, that in some cases social scientists are doing such an excellent job that we forget that actually there are some technical challenges that need to be solved. So for example, there's a whole movement about community-led total sanitation, which you're probably aware of, which is about, very much from a social science side, encouraging people to come up with their own designs of latrines and making sure that they're acceptable and affordable and constructible by the local people. But actually, we've done some research, and some of those latrines don't actually work very well from a technical standpoint, because there was no sort of engineering component to that or advice to that. So yeah, I take your point. I think again, the engineers need to be working directly with the social scientists, but we can't forget the technical challenges that exist. Yeah.
Thanks, Mike. And thank you all for your questions online and in the room. I'm sure the discussion continues. You've given us a lot of food for thought there. You must be exhausted, Mike. Please rest your feet. Okay, so I've got the pleasurable duty now to invite Professor Sabirti Tripathi to give a vote of thanks.
Thank you, Mike. It is clear from the quality and enthusiasm of that presentation why you are such an appreciated lecturer by your students. Hello, everybody. My name is Sabitri Tripathi. I take pride in having been asked to deliver Professor Templeton's vote of thanks in person, all the way from Kathmandu, Nepal, where I am a professor at Nepal Engineering College. When I first met Michael Templeton in 2007, or Mike as he is known, he was just a young doctor, freshly recruited to lecture at Imperial College, and I was not yet established as a researcher at my university in Nepal. I should say that it is not always easy to be an academic or a woman in a low-income country such as Nepal. I remember our first collaboration was working on a project to provide safe drinking water and sanitation for slums and squatters in Nepal, funded by British Council with Mike as the UK partner. I was new to research and Mike took on the role of my mentor. He taught me how to write research proposals and papers and prepare for conferences. He gave me every opportunity he could help me to develop my career. Our partnership grew over the years, and I helped coordinated his research projects in Nepal. Thanks to our many successful collaborations, I have had the opportunity to grow my network internationally, even featuring the Women of the World UK campaign. Mike has always strived for our partnership to be equitable. In fact, I think this is a key personality trait of his. It is present both in his work ethic and the nature of his work. His research is constantly aiming to improve the lives of the poorest in society, like the slum dwellers and squatters from our collaborations. We forget that many people have no choice but to drink dirty, unsafe water and don't have toilets, spreading the succumbing to disease. Imagine yourself for a moment living with the lack of hygiene and comes with not having a toilet or clean water. You would be desperate for someone to address the situation, but not many people would be interested in helping. There is not much glory in toilets. And yet there is a crucial need for sanitation research in developing countries. It takes a certain kind of person to appreciate the breadth of the water and sanitation problems that we face in low-income countries. The kind of person with vision to see through the chaos that slows our development down. It takes someone with patience, dedication, and empathy for the people who live in the chaos to find solutions that will benefit and empower them. Yeah, it takes an astute person with great social skills and tact to converse with both slum dwellers and politicians alike in a foreign culture. It requires passion to persevere, to see projects through these complicated and sometimes hostile environments. And of course, it takes a leader to drive these projects forward year after year, inspiring student after student to further this field. Mike is such a person. His dedication to his work through his research, his colleagues and students has led to significant impact on the ground in developing countries. And by shaping policies and implementing novel technologies, he has improved the prospects for those living with poor water and sanitation. It has earned him many accolades along the way, culminating in today's inauguration as Professor of Public Health Engineering. He is now a long way from the young doctor I first met and has become a recognized leader in this field. But to me, he is always my mentor and my friend. Ladies and gentlemen, please give a round of applause for Professor Templeton. Thank you.
It's okay, you can go, it's fine. You want to take a picture together?
Oh, come around later. Yeah.
Sorry. Anyway, that brings us to the end of Mike's inaugural lecture this evening. You're now invited to a drinks reception just right outside this lecture theater. It will be a good opportunity for refreshment, but also fellowship. And Mike assures me that he's happy if you'd like to take a picture with him out there. So thank you very much online. Thank you in the room for coming. And see you later. Thank you.